Sarah spent $5,000 on Instagram ads last month. How many cars do you think she sold? Let's find out using regression. This video covers it all. 2 marketing channels, 5 months of data, 1 equation to rule them. Let's go. Meet Sarah. She runs a car dealership in the US. Every month, she spends money on Instagram ads. And she's got one question on her mind. Does any of this actually increase her car sales? Here's 5 months of her real data. Somewhere hidden inside these numbers is the answer. And regression is how we find it. So what is regression, really? 3 simple steps. Step 1, scatter the data, plot Sarah's months. Instagram spend on the x-axis, sales on the y-axis. Step 2, draw the best line. One straight line that gets as close as possible to every single dot. Step 3, use it to predict. Spend $5,000 on Instagram. Read off the line. And there's your predicted sales. That's it. The line is your prediction tool. No more guessing. Here's the equation behind everything we just saw. Y equals beta 0 plus beta 1x plus epsilon. 4 parts. Learn all 4 and the rest of this video is easy. Y is what we're trying to predict. Sarah's monthly sales in thousands of dollars. Beta 0 is the intercept. The starting point, sales when Instagram spend, is 0. Beta 1 is the slope, the effect of advertising, how much sales rise for every extra $1,000 spent. And epsilon is the error term. Everything we can't explain, random noise, holidays, competition. One thing to remember, the Greek letters beta are the true values for the whole population. We never actually see them. All we get are estimates called B0 and B1. Now, which kind of relationship is Sarah's? If beta 1 is greater than 0, that's positive. More ads, more sales. If beta 1 is less than 0, that's negative. More competitors, fewer of Sarah's customers. And if beta 1 equals 0, there's no effect at all. Like the day of the week, probably doesn't move car sales. Sarah's hypothesis, beta 1 is greater than 0. She thinks Instagram boosts her sales. Let's see if she's right. Here's the full journey, from theory to data. We start with the population model, y equals beta 0 plus beta 1x plus epsilon. The true values here are unknown, forever. So instead, we use sample data, Sarah's real months of numbers. That's what we actually have. From that, we build the estimated equation. Y hat equals B0 plus B1x, our best estimate of the truth. And finally, we interpret and predict. Use those numbers to actually make decisions. Here's the key insight. We never know the true beta values. We only use Sarah's data to make our best estimate. So, how do we actually find that best line? It's called the least squares method. First, imagine trying thousands of possible lines. Then, measure the vertical gaps. We call these residuals. And finally, pick the one line with the smallest sum of squared gaps. In one sentence, find the line that minimizes the total squared distance from every point. That's the goal. Here's the formula behind everything we've calculated so far. B1 equals the sum of xi minus x bar multiplied by I minus y bar, or divided by the sum of x minus I minus x bar squared. And once we have B1, B0 is easy. Y bar minus B1 times x bar. That's the y-intercept for our estimated regression equation. Let's calculate the regression coefficients, B0 and B1, by hand. Step 1, find the means. The sum of y is 260. The sum of x is 15. Divide each by n, which is 5, X bar equals 3, Y bar equals 52. Step 2, find the deviations. For each month, subtract the mean from the actual value. Month 1, 45 minus 52 equals negative 7, and 2 minus 3 equals negative 1. Step 3, multiply the deviations. Month 1, negative 7 times negative 1 equals 7. Repeat the same process for the remaining rows. The total is 29. Step 4, square the x deviations. Negative 1 squared equals 1. Add them together and we get 6. Step 5, calculate B1, the slope. 29 divided by 6 equals 4.83. Step 6, calculate B0, the intercept. Y bar minus B1 times X bar, 52 minus 4.83 times 3, giving us 37.50. So our estimated regression equation is y equals 37.50 plus 4.83 times x. In plain terms, for every extra $1,000 spent on Instagram, sales go up by about $4,800 on average. All right, pause the video here. Open Excel. Let's do this together. Click the Data tab, then Data Analysis, then Regression. For Y range, select your sales column, including the header. For X range, select your Instagram spend column, including the header. Tick labels, choose New Worksheet, then click OK. You should now see 3 sections: Regression Statistics, ANOVA, and Coefficients. Don't see Data Analysis? Go to File, Options, Add-ins, Analysis ToolPak. Click Go, tick the box, then click OK. Come back when you're ready. Here's what Excel gave us. Y hat equals 37.5 plus 4.83x. B0 is 37.5, the intercept. When Sarah spends $0 on Instagram, expected sales are $37,500. One quick caution: zero spend is outside our data range, so treat this as a baseline, not a real forecast. B1 is 4.83. The slope for every extra $1,000 spent on Instagram. Sales increase by $4,830 on average. This is the most important number in the model. Always interpret this coefficient first. Now, let's make a prediction. If Instagram spend is $5,000, Y hat equals 37.5 plus 4.83 times 5 equals 61.67. Predicted sales, $61,670. One number in, one prediction out. That's regression, doing its job. But wait, is this relationship actually real? Let's test it. Our null hypothesis, beta 1 equals 0. Instagram has no effect. Our alternative hypothesis, beta 1 does not equal 0. Instagram does affect sales. Here's the decision rule. Reject the null hypothesis if the p-value is less than or equal to alpha. Here, our p-value is 0.01. Our alpha is 0.05. 0.01 is smaller. So, we reject the null hypothesis. Instagram has a statistically significant effect on sales. Quick question for you. Sarah wants to predict sales. If she spends $3,000 on Instagram, what's the predicted sales amount? Pause the video for 5 seconds and work it out. Here's the answer. Y hat equals 37.5 plus 4.83 times 3 equals 52. If Sarah spends $3,000 on Instagram, her predicted sales are $52,000. If this is finally clicking for you, drop a like right now. It genuinely helps. Coming up next, part 2, how good is this model? Really? We'll break down SST, SSR, SSE, and the one number that tells you whether you can actually trust it. Hit subscribe if you haven't already. Let's keep going.